All right, so welcome back. Hopefully you had a good first week and things are going along okay in terms of the trig. I do know that there is a question about one of the homework problems, specifically the hamster problem that people would like to see. And that one I think came from the little video homework, but we can go and look at that. Before I jump over there, any other homework questions people are curious about? Because I'd kind of like to just kind of make my list so that when I jump over there and do the screen share, I've kind of got everything ready to go. All right, well, I'm not seeing anything or having anybody ask, so I'm going to go ahead and share my screen, and we're going to go look at that homework problem, specifically the one about the hamster. So, all right, so hopefully everybody can see it now. But here we've got this hamster's running in a wheel of radius 13 centimeters and spins the wheel at 20 revolutions per minute. And we want to figure out what's the angular velocity of the wheel and at what linear velocity is the hamster running. Okay, well, let me switch to the board. I'm still going to share this window, but I'm going to change my screen to that of the whiteboard. So hopefully you'll see that up in the corner. So now we should be on the whiteboard. Hopefully you see that. But let's write down the information here. And once we get all the information written down, we'll go to the whiteboard. I'll remove the screen, and this way we can kind of work it out. So obviously your problem might have a little bit different numbers, but the same idea. So I'm going to use these numbers. And so we've got the wheel has a radius of 13 centimeters. So I'm going to go ahead and write that down, 13 centimeters. And then we're doing 20 revolutions per minute. And what we want to find, the two parts to this question, the first is we want the angular velocity. And it says we want this in radians per second. And then we also want to know the linear velocity of the hamster. And it wants that in centimeters per second. So there's everything that we need. So let's see if we can calculate it. So I'm going to turn off the computer. So now we hopefully should be able to see on the board what we're looking for. All right, so let's start with the first part, angular velocity. So what does angular velocity mean? Do you remember? What do we actually need to calculate an angular velocity?
Change in angle over change in time.
All right, thanks, Kai. Perfect. So we need to know the angle and we need to know the time, so we can just divide it. And I see Amber just threw up there on the chat, angle and time. So let's think about angle and time. So the only piece of information that we have that involves time is this 20 revolutions per minute. But that's actually what's going to give us our angle over a given amount of time. The only problem is a revolution isn't an angle. But think about what we know. We know that a revolution is one time around, right? So if we do one big cycle, that's one revolution. And what's the angle in one revolution?
360.
All right, so in degrees, it's 360 degrees. But in radians, and we want radians, right? They're asking us specifically for an angular velocity in radians per second. And that's where we want to use the 2 pi. So depending upon which of the two we want, we use that proper amount. So for this one revolution is equal to 2 pi radians. So if I want to know how many radians 20 revolutions is, I just need to multiply this by 20, because each one of those revolutions is 2 pi radians. I've got 20 of them, so 20 times 2 is going to be 40 pi. So that's the angle that we're actually going through here in 1 minute. It's 40 pi. Now, obviously, your number is going to be a little bit different. Like if you had 15 revolutions, you do 15 times 2 pi. If you had 23 revolutions, you do 23 times 2 pi. But whatever it is, however many revolutions, you just multiply by 2 pi. All right, so that's our angle. But now we need to know how much time that took. Well, if you come back and you look at the beginning, it says 20 revolutions per minute. So we do 40 pi in 1 minute. But I want this in radians per second. So instead of 1 minute, I'm going to use the number of seconds that are in a minute, which is 60. So my angular velocity, remember we use this curvy W thing, it's the omega. It's going to be my angle over time. So my angle was 40 pi. My time is 60 seconds. And so we end up with, I'm just going to write it as a reduced fraction, 2/3 pi radians per second. And I could go ahead and get a decimal approximation for that. It's going to be slightly more than 2. It's going to be right around, I'm going to guess about 2.2, or yeah, something around 2.2-ish. But that doesn't really matter. We can just leave it like this for right now. Obviously, with your numbers, you're going to go ahead and use your calculator, get the decimal approximation, and put it into my open math. All right. So Amber just asked, does anybody know if it wants to answer as a decimal, reduced fraction, or whatever? I can pull mine up again. And it just says enter it as a mathematical expression. So I would probably go with a decimal approximation, but I don't really know. All right, so there's our angular velocity. Angular velocity is actually really straightforward. You define angle and divide it by time. This one was just complicated because we had to do some conversions. All right, so let's move to the second part then. So the second part is we want to know the linear velocity of the hamster. So how fast is that hamster actually running to make this thing spin at 20 revolutions per minute? All right, well, linear velocity, that's our guy V. And so we're going to use the formula that involved V and omega. So we had a formula that we developed that looks like this, that V is equal to R times omega. And so V is your linear velocity. R, that's your radius. That's how far away we are from the axis of rotation. And then omega is our angular velocity. So now we know these quantities. We know the radius. It's 13 centimeters. We just calculated our omega. It was that 2 pi over 3 radians per second. So if we multiply those together, that'll get our linear velocity in centimeters per second. And that's what they asked us for. So we don't have to do any more conversions here. It's just a matter of doing this computation. So let me just grab my calculator here real quickly and we can figure out what that is. So I get approximately 27.2 centimeters per second. well, again, just like before, yours might be a little bit different because you'll have a different radius perhaps, or a different number of revolutions per minute, but it's found the same way. You're just going to take whatever your radius was times the omega that you calculate in part A. All right, so does that make you guys feel a little bit better about the hamster problem? Not necessarily hamsters in general. All right, I'm getting a couple of thumbs up. Cool. Any other homework problems we want to look at before we keep moving on in Trig story? All right, so Mariola, number 12, is that from the same homework set, the video 7.1? Okay. So let me pull up number 12. We'll share the screen again. All right, so it's another pesky hamster, huh? So it says we have a hamster that's running at a speed of 5 centimeters per second in a wheel of radius 9 centimeters. And we want to calculate A, the angular velocity of the wheel, again in radians per second. And then we want to know how fast the wheel is going to be spinning in revolutions per minute. So if this feels kind of similar, it should. Obviously, it's still a hamster spinning a wheel, but basically now we're just going backwards. We're being told the velocity, the linear velocity. This hamster is moving at 5 centimeters per second. And again, we have a wheel with a radius. This one's smaller, only 9 centimeters, but it's still kind of the same idea. So we're going to try to find omega and the number of revolutions per minute. All right, so there's all the information from this guy. So let me stop sharing so we can look at the board again. So we've got our V and we've got our R. We're going to use the exact same formula. We're just going to solve for omega now. So we've got V equals R times omega. So omega is V over R. So that's going to be 5 centimeters per second divided by 9 seconds, or sorry, 9 centimeters. And so that gives us an omega of 0.56. And this is going to be radians per second. And the reason that I know that it's radians is what we call a dimensionless unit. So there is nothing to put on there. It's just radians. All right, so there's our omega. There was the first part. And notice that we're just using the same formula. We just have different information. So now if we want to go to revolutions per minute, we have to convert this guy to revolutions per minute. So we're going to do kind of the same thing. We're going to remember that 1 revolution is 2 pi radians. And also the fact that 1 minute is 60 seconds. So I'm going to go ahead and convert this. So we have 0.56 radians per second. I'm going to multiply by the conversion factor that contains seconds and minutes. So I'm going to have 60 seconds for every 1 minute. And I do it this way because I need the seconds on top to cancel with the seconds on the bottom of the original units. So if I do this multiplication, I'm going to get the number of radians per minute. So we're getting closer, but now I need revolutions. Well, again, I know that 1 revolution is equal to 2 pi radians. So I'm going to multiply by the conversion factor 1 revolution over 2 pi radians. And again, I did it this way so that my radians cancel and I'm left with revolutions. So if I multiply this out, I'm going to be left with just revolutions per minute. So anytime you're going to convert from one thing to another, you always multiply by the ratio that contains the conversion factor. And we were doing this like on day one when we were doing radians to degrees and vice versa. So if you remember how we did that, this is really the same idea. It's just it's holding a different conversion because we're doing different units. Well, anyway, we can now do this multiplication. So let's see what my trusty black box says. I've got 0.56 times 60 divided by 2 pi. And I get 5.35. And so this is the number of revolutions per minute. So this is going much slower. Okay, we're getting a much lower number of revolutions per minute than the other problem. So this is a sleepy hamster, maybe. Anyway, so does that make a little more sense? Getting a couple of thumbs up. I just want you to realize that it's just the same problem, just the other direction. We didn't do anything differently. We still use the conversion factors. We still use the V equals R omega. We just had different information that we were putting in. All right. So any other homework problems at this point? All right, so William just put up, he had trouble with number 10 on 7.2. All right, well, let's go take a look at that. So I'm going to share my screen again. And then we'll go find that guy. My computer is very sleepy, much like that second hamster. Oh, I probably should have asked. Was it the video assignment or the regular? And I can't see the chat window right now. So William, if you could just real quick. Oh, actually, never mind. I know it's not the video because there's only 2.
It was just the last problem on the right triangle trigonometry.
Okay.
Yeah.
Thank you.
Yeah, totally.
Does that look right?
Yeah, that's the one.
Okay. So we've got a survey team trying to estimate the height of a mountain above a level plain. From one point on the plane, they observe that the angle of elevation to the top of the mountain is 24 degrees. From a point 1,000 feet closer to the mountain, they find that the angle of elevation is 28 degrees. How high is the mountain? Well, let's write down the information and then we'll actually see if we can calculate this. So we've got 24 degrees and then it goes to 28 degrees. When we go 1,000 feet. All right, let's go to the board. So I like to draw pictures, even if they're really dumb and silly. But there's going to be our plane. There's our mountain. Of course, there's snow on top because it's the winter. So here's what we know. So somewhere over here, surveyor looks up to the mountain and sees that that angle of elevation is 24 degrees. So then she goes 1,000 feet closer. So let's, right here, there's 1,000. And this time notices that the angle is a little bit bigger. It's actually 28 degrees. So there's a picture that's got all the information. And what we want is we want to know how high is this mountain. So I'll go ahead and call it H. All right. So somehow I got to figure out what that H is. Well, hopefully you see two right triangles in here. We put our little 90-degree mark here. We've got a right triangle there. The right triangle that contains the 28 degrees and also the one that contains the 24 degrees. So let me rewrite them. Let me draw them again separately. So here's the easier one, the kind of the smaller one. This is the interior guy. So we've got our H, we've got 28 degrees. And I don't know anything else about this. I mean, I guess I do know the angle that's up top. I can figure that by subtracting 28 from 90. But what I really want is some sort of a side. And the side I'm going to go with is this guy, X. I don't know what it is, so I'm just going to put an X. But the reason I want to know about this side is that's the side of the larger triangle, or that's part of the side of the larger triangle that I know something about. Because if I look at that larger triangle with the 24 degrees, again, I know its height is H, but now I know its length down here. It's going to be that X from the smaller triangle plus 1,000. Okay, yay. So we've got this. We actually have two unknowns. The one is the height that we're curious about, and the other one is this length X. But hopefully you remember from algebra that if you have two unknowns, in order to find them, you need to have two equations. So let's build two equations. Let's get one for each of these triangles using one of the trig functions. So looking at this picture right here, this first one, with that angle of 28, which trig function involves these two sides, the ones I've labeled H and X? And I said trig function, it's actually functions there too. So Amber, William, they just threw up tan, right? And then we got a cotangent and tangent from Mariolan. Yeah, so we can use tangent or cotangent, either one. I suggest we use tangent because it's the, one of the big three. So what I know is that the tangent of 28 degrees is equal to H over X. I can do the same thing for the second triangle, the bigger one, and we're going to use the exact same function. This time we've got the tangent of 24 is equal to H over X plus 1,000. All right, so there are my two equations, and now I just need to solve this for H. So what I'm going to do, first I'm going to get rid of the fractions just because I can. So I've got X tangent of 28 degrees is equal to H. And on the other side, we've got X plus 1,000 times the tangent of 24 is equal to h. And so we can do the old substitution thing where we solve for one letter and plug it into the other. And maybe, hopefully, you already notice that these are both h equals, which means I can just equate those two things together. So we'll get x tangent of 28 degrees equals x plus 1,000 times the tangent of 24 degrees. And there's an equation that involves only x. So I can go ahead and solve that for x. We're going to distribute like we normally do. So we get x tangent of 28 equals x tangent of 24 plus 1,000 tangents of 24. Now I want to move all of my x's to one side. So I'll move this bit from the right to the left. So we get x tangent of 28 minus x tangent of 24 equals 1,000 tangents of 24. And I know that this probably feels a little weird because you look at this and you've got x times these tangent stuff. Just realize that these are numbers. It's just like if we had 7x minus 2x. The way we do that is just subtract the two coefficients, the two number parts. So we're going to get tangent of 28 minus tangent of 24. We're going to get that many x's. So once we get that number, all we have to do is divide. So we're going to get x is 1,000 tangents of 24 degrees divided by the tangent of 28 minus the tangent of 24. In algebra terms, we factored out an x, and then once that thing was removed, we divided by that whole big expression. So this is ready for us to use our calculator. But what I would do, I actually wouldn't calculate just yet. I would go back and take this, so this thing that we found for x, and I would actually put it back into the equation to solve for h, because h is what we want. We want the height of the mountain. Remember, x was how far away the survey spot was. I don't care about that. I care about the height. So I would take this and multiply by the tangent of 28 degrees, and then do it all at once in my calculator. So let me just tell you what my calculator would tell me for this number. Make sure you're in the right mode. I need to be in degree mode, right? So we're going to get 1,000 tangents of 24 times tangent of 28. And we're going to divide from that the difference of tangent of 28 and the tangent of 24. And I got a number approximately 2737.4. And I seem to recall that these were in feet. So that mountain is sticking up 2,700 feet above the plain. Again, your numbers are going to be slightly different, but it's still kind of the same. All right, so Amber just asked, when would you put your calculator in Radian mode? Would we have had to do that in the hamster problem? In the hamster problem, no, because we weren't actually taking any trig function of the angle. But if we wanted to say take the tangent of an angle like pi over 3 or pi over 6, then we'd need to be in that mode. So it's only when you're actually using one of the trig functions that you have to make sure you're in the right mode that matches whatever units your angles are in. All right, so we feeling better about this one? This is a tricky problem, no doubt about it. It's tricky for a couple of reasons, but primarily because we have to create a system of equations.
But you'll see this a lot, actually, that when we go and we try to solve an applied problem, that we have to use these tricks from algebra. And solving systems is one of the big ones, because you'll notice, like with this problem, I created a variable that was nothing I was looking for. And yet without it, we couldn't have done the problem. And so this is a big trick that we use all the time, especially in trig, because trig is always when we're using the trig functions, we need a ratio of two things. Sometimes we know one of them, sometimes we don't. So get used to that. Throw in I like to call it a dummy variable. It's just a placeholder that eventually we get rid of, but sometimes we need. All right, any other homework questions, or are we ready to kind of move along? Because I don't know about you guys, but I'm kind of ready to move along. I'm super excited. This is one of my favorite things, what we're about to do. I just really wish that I could be in person with you guys, because it tends to use a lot of whiteboard. But all right, well then we're going to go ahead and keep moving along now that we've learned a little bit about what triangle measurement really is, and we've talked a lot about angles. We then introduced the 6 trig functions. Remember your good old SOHCAHTOA way of remembering your sine, cosine, tangent as ratios of sides. But the big 3 also have their buddies, cotangent, secant, and cosecant, that are reciprocals, right? But we have 6 trig functions. And the way that we've defined them is awesome. It works super, super, super well when we have a right triangle. But the problem is we don't always have right triangles. We still want to be able to use these things. And specifically, we need to deal with the fact that sometimes our angles are bigger than 90 degrees. Like the way that we created our trig functions using triangles, we're really restricted. We can only have angles between 0 degrees and 90 degrees, and not including 0 or 90, right? You can't have a 0 degree angle in a right triangle, and you can't have a second 90 degree angle in a right triangle. So we need to define this in a little bit different way. And to do this, we're going to use what's called the unit circle. Now, a unit circle is a circle, obviously, and unit just means that its radius is 1. So we're going to be looking at a circle whose radius is 1, and I'm going to show you how you can use that circle to find the trig function values for any angle. And especially this is going to be useful for angles that are outside of that 0 to 90 degrees. So that's where we're going today, and we'll look at those special angles again, and I'll show you where the unit circle ties in and all that good stuff. All right, so let's go to the whiteboard.
So let's start with just a circle. And we're going to make it unit. So the other thing that I need to tell you is where that circle is going to be located. But we're going to make it so that the center of that circle is at the origin. Okay, so this is going to be our unit circle. So that means that we're coming out on the left and right to plus or minus 1. And we're also going up or down to plus or minus 1. All right, so there's a unit circle. Now, a couple things about it. First of all, if I've got some random point over here, we're going to label that guy x comma y. We do know that it's a distance of 1 away from the origin. And we also know the equation of this circle. For those of you who have already taken 103b, anybody remember the equation of a circle, specifically one centered at the origin with a radius of 1? All right, so Devin just threw in an equation for us. It says x minus h squared plus y minus k squared equals r squared. And that's exactly the one we're going to use. We're just going to put in the information we know, that the center is 0, 0. So the h and k go away, and then the r is 1. And so what it does give us is an equation that looks like this. It's x squared plus y squared equals 1. So a couple of people have put that into the chat. And that's exactly it. It's x squared plus y squared equals 1. So we know a lot about this circle. And that's what we've got. Now, how we're going to relate this back to the trig function is I'm going to draw a right triangle here. So in this same picture, I'm going to make a little right triangle. So I already know that the hypotenuse is 1. The long side is 1 because it came from the radius. And so what I need now are the lengths of sides for the other two. But those are just our coordinates, because that's the whole point of coordinates, is it tells us how far we're going to go left and right. So this horizontal one is x, and this vertical one is y. So I'm going to redraw that down here because my picture is getting a little bit cluttered. But that's our picture now. And we also have some theta that's bringing us to that point. All right, so this triangle, it's really just the picture from right there. I want you to notice something. Do the Pythagorean theorem on this triangle. Good old a squared plus b squared equals c squared. And check it out. You got x squared plus y squared equals 1 squared. Ta-da! Yeah, that's actually where the equation from circles come from, is just looking at the Pythagorean theorem. So if you didn't know that, fun fact. All right, now let's think about defining all of our trig functions using this right triangle. So I'm going to make a list here. So the sine of theta, if we do our good old SOHCAHTOA, it's the opposite over the hypotenuse, which is just y. So on the unit circle, if you knew the point, the y-coordinate is the value of the sine of theta. Similarly, if we do cosine, cosine is adjacent over hypotenuse, which is just going to be x. So this is really the reason that we like the unit circle, is that on the unit circle, any point is just going to give you the cosine and the sine in that order. And this is how we're going to get angles bigger than 90 degrees and figure out what their sine and cosine are. We're just going to look on this picture and figure out the coordinates of the points. And whatever those coordinates are, the x coordinate is the cosine and the y coordinate is the sine. All right, well, the other four, if we look at tangent, tangent is opposite over adjacent, so that's going to be y over x. The other three, we're going to get cotangent. Cotangent is just tangent flipped over, so that's x over y. Secant is just cosine flipped over, so we're going to get 1 over x. And cosecant, we do the same thing with sine, and we get 1 over y. So that's how we're going to define the 6 trig functions in terms of the unit circle. And like I said, this is going to open it up so that we can get lots of different angles. And in fact, we're going to start with the easiest angle in the world, but one that's impossible to find using right triangle. So before we go there, is everybody okay with how I got these? I'm just using this right triangle that we built from the picture. So I'm getting some thumbs up. Looking good? All right, well, I will take silence as so far so good. All right, well, before we jump to that, I want to talk about this form that I put up into Canvas just a little bit ago. So hopefully you got the message earlier today. If you didn't, that's fine. I'm going to go ahead and show this to you. I'm going to share my screen again. But I have a form that when I meet in class, I go ahead and give to everybody because we work on this and we fill it out. So I'm going to go show it to you. I'm going to go click on Files. You can get to it this way as well. I'm going to click on Files. It's going to bring a list of files that I've put up into class. And I'm going to go to this one called Trig Values Chart. So we'll go ahead and pull the sucker up. So hopefully some of you were able to print this out. If not, that's fine. I totally understand. You might not have a printer at home or anything like that. But what we can do with this, let me show you what we're going to do. So you notice there's a column here that says degrees, and there's a column that says radians. This is obviously going to be the angles that we use. So somewhere in here, for example, is going to be 45 degrees. So 45 degrees is one of the special angles like we saw before. We're going to put its radian equivalent. And then across this column, or sorry, across this row, we're going to put the trig function values for that angle. So, you know, I bring up pi over 4 because that's one that we actually know. We did that last time. We saw that the sine was root 2 over 2, the cosine was root 2 over 2, the tangent was 1, the cotangent was 1, and the secant and cosecant were both root 2. So we're going to use this just to sort of keep track of all the different angles we do. And when it comes time for us to actually do this, I'll tell you which row to use and all that. But we're going to try to build this because this is going to help us see patterns. We're going to see all kinds of patterns once we look into these columns. And we'll see some patterns that are going to help us remember these special values. All right, so if you didn't get a chance to print this out, if you have the opportunity to do so, I highly recommend it so that we can kind of work on filling this out. Otherwise, just take good notes and then maybe you can kind of create your own chart. All right. So let's go ahead and see if we can do some angles. So if you've got that chart, we're going to do the very top row. And the very top row, we're going to start with 0 degrees. All right, so what is that in radians? Oh, so Benjamin just asked, was that starting 7.3? Yeah, unit circle stuff is in 7.3. And I apologize. I'm just going to tell you flat out, I don't exactly follow the book. So like what I'm going to do is kind of a combination of 7 and 3 and 7.4. I rarely will tell you what section we're starting because, well, 2 reasons. One, well, really 1 reason, because I don't know. I don't know what the sections are. I don't know what's covered where. I kind of do it in my own order, which is a little bit different. But yeah, we're somewhere in 7.3. So if we go back to the 0 degrees, Kiva went ahead and threw up that that's actually 0 radian. So you want the top row to start with 0, 0, because 0 degrees is 0 radians. And you notice that I put the degree symbol for the degrees, but I don't put anything on radians because radians are dimensionless. All right, so now we're going to figure out sine, cosine, tangent, cotangent, secant, and cosecant for 0. So the first thing I'm going to do, I'm going to redraw my unit circle. And we saw that we can get all of the trig function values if we know the point on the unit circle that corresponds to the angle. So imagine I have an angle of 0 degrees. Then the terminal side is going to be the same as the initial side, which is going to be right here. And that intersects the unit circle at this point. So what are the coordinates of that point? What's the ordered pair for that? So I'm seeing a couple of responses. I've got 1, 0. I've got 0, 1. So I'm glad you guys are seeing that there's a 0 and a 1. But this point right here is 1, 0. We're going to the right one, and we're not going up and down at all. All right, so here we go. In terms of getting sine, cosine, so on, we saw that the sine is equal to y. I'm going to write this back down here. So sine is y and the cosine is x. So the y coordinate of this is 0. The x coordinate is 1. So as you're going across that row, the next two entries should be 0 and 1, because that's our sine and our cosine respectively. So you just found the sine and cosine of an angle that never exists in a right triangle. Right? You can't have an angle of 0 degrees. Otherwise, the triangle doesn't exist. And yet, we can still get a sine and a cosine value. So that's the power of the unit circle. All right, well, let's find the other ones. So let's think about tangent. Again, tangent was y over x. So we're going to take our y coordinate and divide by our x coordinate. So 0 divided by 1, that's 0. So we get that the tangent of 0 degrees, or 0 radians, is also 0. So then if we go to the cotangent is, well, flip this over. So we're going to have x over y, which in this case means we're going to take the 1 and we're going to divide by 0. Well, that clearly is a problem. And so what we're going to put here, I'm going to put UND for undefined. So the cotangent doesn't exist at an angle of 0. And it doesn't exist because we're being forced to divide by 0. Huh, okay, well, there's our tangent and our cotangent. So then if we go to secant and cosecant, and I apologize, I ran out of space, so I'm going to do this down here. So this is just a continuation of the 0, 0, but we're going to have secant and we're going to have cosecant. So secant, if you go back and you look, is actually 1 over x. Well, the x coordinate is 1. So the secant of 0 is also 1. And then cosecant is 1 over y. Well, y is 0. We're dividing by 0 again. So that's going to be undefined. So the very first row of your sheet should read 0 degrees, 0 radians, and then 0, 1, 0, undefined, 1, undefined. All right, so there's 0 degrees. So even though that angle doesn't actually exist in right triangle, we can still figure out sine, cosine, tangent, all the different trig function values for it. But notice that there are a pair of them that do not work. All right, so any questions on how we built that using that point on the unit circle? We good? Thumbs up. All right, so let's turn our attention to another one, another angle. I'm going to look at 90 degrees. So on your chart, I want you to skip 3 lines. So we had 0 degrees. Then I want you to have blank, blank, blank. And then we're going to put 90 degrees. So this is what it should look like. There are going to be 3 angles that are between 0 degrees and 90 degrees that we're going to put in. You already know them. They were the special angles from the right triangle, so they're going to be, yeah, you can go ahead and put them. This is 30 degrees, 45 degrees, and 60 degrees. So this is what it should look like for the first 5. Okay, so 0, 30, 45, 60, and 90. These middle 3 we'll fill in a minute, but let's do the 90 degrees first. So I'm going to go ahead and continue this over here, and I'm going to try to see if I can actually get enough space for everything. I think we're going to be good. All right, so there was our 0 degree row that we just calculated. So now let's go to 90 degrees. So let's go to the unit circle, just like we did before, and let's figure out what point is on the unit circle if we have an angle of 90 degrees in the standard position. So 90 degrees means we've done a quarter of a rotation, which means our terminal side is pointing straight up. So that means that the point where we're intersecting the unit circle is this one up here. So the coordinates on that one, we're going nowhere left and right. That's a 0, comma, and then we're going up 1. So that's the point 0, 1. So we're going to do exactly the same thing that we did before to fill in this chart. So let's start with radians. How many radians is 90 degrees? Do you remember what a quarter rotation gives us? All right, Mariola just threw in pi over 2, followed very quickly by Kiva and Kai giving me the same thing. So 90 degrees, that's pi over 2 radians. All right, so this row starts 90 and then pi over 2. And now let's get our sine, cosine, tangent, and so on. Okay, so the sine, that's the y coordinate, which means this time it's 1. So the y coordinate is 1. Cosine is the x coordinate, which was 0. So notice that the sine and the cosine swapped. But that shouldn't surprise you, because remember that whole complementary angle thing? That's what's happening here. 0 and pi over 2 are complementary angles. So we know that the cofunctions are going to swap. Well, since we know that, let's do this real quick. Let's take tangent and cotangent and swap them. So tangent is now undefined and cotangent is 0. And you can see that from their formulas. Tangent was y over x, so 1 divided by 0, which is undefined. And then cotangent was x over y, and 0 divided by 1 is 0. And then we can do the same thing with secant and cosecant. You can swap those. So we get undefined and 1 for those two respectively. All right, so there's the 5th row. The 5th row of your chart should read 90 degrees, pi over 2, 1, 0, undefined, 0, undefined 1. All right. So, feeling okay? Not a big deal. Well, let's keep filling in those rows. So we're going to skip 3 more rows. So after 90 degrees, I want blank, blank, blank. And the next one we're going to look at is 180 degrees. Okay, so we've got 90, blank, 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 and then 180. So I'm just going to save some space in here. Obviously, this isn't what it's going to look like on our form, but I just don't want to have to keep redrawing this thing. So we're also going to look at 180 degrees. And in terms of radians, that's pi. So Amber just asked, does undefined and DNE say the same thing? Yes. DNE does not exist. That means the same thing as undefined. I believe on my math, on my open math, you're going to need to type in DNE. Same thing. All right, so let's look at 180 degrees, which is the same as pi. And now we're actually on the left on the unit circle. And this one, the coordinates of the point are -1 and 0. So let's get all of the trig function values for this guy. So sine is the y, 0. Cosine is the x, -1. Tangent, that's 0 over -1, y over x, so that's 0. Cotangent, that's going to be x divided by y, which is -1 divided by 0, which again is undefined. Okay, so yes, Juan Carlos, 3 spaces between 90 and 180. Always 3 spaces as we go through this. Okay. So it shouldn't look like this on the chart. Like I said, I'm only putting it here to save myself space because I have a small whiteboard. But it should be 0, space, 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 90, followed by space, 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 180. All right, so secant is 1 over x, and 1 over -1 is -1. And cosecant is 1 over y, which again is undefined. So look at that row, the 180 degree row. When you compare that to 0, what you get is the same thing, except for the signs have changed. They're now negative. And when I say signs, I mean plus or minus signs. And so we've got -1 instead of 1. All right, so there's 180 degrees, which is also impossible to have in a triangle of any kind. Now, after 180, leave 3 more spaces, and we're going to go to 270 degrees. So after 180, 3 blank rows, and then we get 270. Now 270, that one, if we convert that to radians, is 3 pi over 2. And 270 is now pointing straight down. So if we do 270 degrees, or 3 pi over 2, we've gone all the way around like this. And now we're pointing straight down. And so the coordinates of this point are 0, -1. Oh, well, let's just build our chart. So sine is the y, that's -1. Cosine is the x, so that's 0. Tangent is y over x, so -1 divided by 0, which is undefined. Cotangent is the other way around. It's x divided by y, so that's 0. Secant is 1 over x, X is 0, so that's undefined. And then cosecant is 1 over y, which is -1. So look at that row, 3 pi over 2 and pi over 2. We have the exact same kind of pattern we saw with 0 and pi. The only thing that changed here were the signs, the plus or minus signs, that go 1 or -1. All right, now if you've been doing the pattern correctly with the skipped rows, you should be able to do 3 more skipped rows and then be on the very bottom row. On that very bottom row, we're going to go 360 degrees. Okay, so the way the chart should look, 0, blank, 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 90, 3 blanks, 180, 3 blanks, 270, 3 blanks, 360. So 360, we've now completed our tour. We're back to where we started. It's an angle of 2 pi. And this row is really easy to do because this row is going to be exactly the same as the first row. 0 degrees and 360 degrees, they're what we call coterminal. Their terminal sides are at the same location, so they share that same point. So we can literally just copy that top row and put that on our bottom. All right, so we now have 5 rows of that chart filled, and you definitely see a pattern with these numbers, and we'll talk more about that pattern after we fill in the remaining bit of this chart. All right, well, let's take a break. I'm actually going to go and see if I can get a white pen that's a little bit, or a whiteboard pen that's a little bit darker. This is starting to run out. Also grab a real quick drink of water. So it's 12:04 on my computer clock. Let's come back at 12:10 and we'll knock out some more rows. All right, so I will see you all in just a moment.
All right, so now we've got the angles 0, pi over 2, pi, 3 pi over 2, and 2 pi. Real quick, just so you know, we call those angles quadrantal angles. I'll write that up on the board. But a quadrantal angle is any one whose terminal side is on one of the axes. And so they're kind of special, which is why they get a name. But we're going to look at some other ones. And we're going to start with our good friend pi over 4, or 45 degrees. So let me go back to the whiteboard.
So again, the angles that we just found, we call those quadrantal. So those are the ones that just show up on one of the axes, where the terminal side is on one of the axes. So just so you know, that's what we've done. Now, the next one I want to do is 45 degrees. And we already saw where that should go on our chart. It should be smack dab between 0 and 90, right? So we have 0, then blank, or 30 degrees, and now 45 degrees. So what is that one in radians again? Do you remember from last time? All right, Kai just threw out pi over 4, thank you. So that's an angle of pi over 4. So if I draw my unit circle, we saw that that was halfway between 0 and pi over 2. So there's our angle of pi over 4. Now, I don't know if you remember this, but we saw that the sine and cosine for these were √2 over 2. So that means that the point on the unit circle this point right there is √2 over 2, comma, √2 over 2. So hopefully you were in class last time, or at least watched the video and saw where we got that. It actually just came from the fact that this is an isosceles triangle, and we were able to calculate that. So we're going to go ahead and put those in for our sine and our cosine. And then we also saw that the tangent and cotangent were both 1 because y over x and x over y, since they're the same numbers, they're both 1. And then the secant and the cosecant, we saw that those were equal to square root of 2. So that's not new. We saw this last time. We're just putting this into the chart. But we're going to use this angle to actually find some other ones on our chart. And in fact, the next one I want to find is this one over here, whose x and y coordinates are similar to the point we just looked at. They're just negative root 2 over 2, comma, root 2 over 2. All right, so before we write anything in our chart, I want to figure out what that angle is. So here's what we're going to do. We're going to use the first angle, that guy pi over 4, to help us find it. And we're going to use the symmetry of the circle to kind of finish everything together. So this angle right here was pi over 4. And notice from the symmetry that if we were to come from the negative x-axis, this would also be pi over 4. But coming from the negative x-axis doesn't really help me. What I need to be able to do is figure out what this angle is from the standard position. So basically, how far are we going this way? But here's where we can use that pi over 4. I know that if I went all the way to the negative x, that's half a rotation, which is pi. But I don't go all the way. I'm stopping pi over 4 short. So what I'm going to do is I'm going to take pi minus pi over 4, which gives me 3 pi over 4. So the angle that we're looking at is 3 pi over 4. Now, where I want this to go in your chart.
Why don't you look at me and I can kind of maybe explain it better with my hands. Okay, so this guy, 3 pi over 4, it's going to go halfway between pi over 2 and pi. So in your chart, you started at 0, come down to the fifth one is pi over 2. And then you had 3 blank spaces and then pi. This one's going to go halfway in between. So it's going to go pi over 2, blank, 3 pi over 4, blank, pi. All right, so that's where this one needs to go. So we're going to have, again, pi over 2, blank, 3 pi over 4, blank, pi.
So I'm putting it directly under pi over 4. That's just because, again, I need to save space. But it's actually going to go halfway in between pi over 2 and pi. All right, so we need to figure out what this angle is in degrees. So we can multiply by the pi over 180, or sorry, 180 over pi. Or we can use kind of a similar argument of we're 45 degrees short of going halfway around. Halfway is 180. So when we subtract 45, we get 135. So you were right, Amber. It's 135 degrees. All right. So I wanted to use this angle just because it's very similar to pi over 4. And because of that similarity, check out how fast this is going to be. So in terms of all the numbers, they're all the same. The only thing that's going to change are some signs. Anything that's just y stays the same. So sine is still root 2 over 2, and cosecant is still square root of 2, because those are only y. The ones that involve only x are now going to be negative. So cosine is going to be minus root 2 over 2, and secant is going to be minus root 2. And then lastly, tangent and cotangent, since they're y divided by x, we have a positive divided by a negative, which makes them big. So if we know pi over 4, we also really know 3 pi over 4. We just have to change a couple of signs. But we're making use of the symmetry of the circle. Well, I bet you can guess where we're going to go next. We're going to do the same thing, but we're going to come over here to the third quadrant and find the angle whose x and y coordinates are both minus root 2 over 2. Well, from the symmetry, this angle again is pi over 4. So this time I want to take pi and add pi over 4, which is going to give me 5 pi over 4. Real quick, let me jump back because I got a question in the chat. Idana just asked, why didn't sine change to a minus? So the reason sine didn't change, sine is only the y coordinate. And the y coordinate here is still positive. So all I'm doing is I'm taking that point and I'm taking its y coordinate, and that's why it stayed positive. So does that make sense? Okay, cool. All right, so this angle is 5 pi over 4. Now the row it's going to go in is halfway between pi and 3 pi over 2. So kind of the same deal. You're going to have pi blank 5 pi over 4 blank 3 pi over 2. Basically, by the time we're done with these, we're going to have every other line filled. So 5 pi over 4. Again, we need the degree equivalent, so you can multiply by 180 over pi, or do the same thing. We're 45 degrees beyond halfway, so you'll take 180 plus 45, which is 225 degrees. All right, so that's the one that's going halfway in between pi and 3 pi over 2. We're going to start it as 225 degrees, 5 pi over 4. All right, now, same story as before. We're going to get the same values with just different signs, plus or minus signs on some of them. So now if we have just x or just y, these are going to be negative. So that's going to make the sine and the cosine both be minus root 2 over 2. Similarly, the secant and the cosecant are going to both be negative root 2. But then when we get to tangent and cotangent, now we're taking y divided by x. Since they're both negatives, a negative divided by a negative is positive. So it's the same values, it's just a different pair of them are positive. All right, so we're almost done with these guys. The last one is going to be the one down here. In terms of the coordinates, this time the x is positive and the y is negative. So this is going to be root 2 over 2, negative root 2 over 2. In terms of the angle now, well, we're pi over 4 short of completing a full cycle. So if we were to do 2 pi minus pi over 4, right, a full circle minus the bit that we're not quite there, getting a common denominator of 4, we'll leave this as 7 pi over 4. And that's going to go halfway between 3 pi over 2 and 2 pi. In terms of the angle, in degrees, same deal. We're 45 degrees short of going all the way around. So if you take 360 and you subtract 45, you get 315 degrees. Well, same story. All the numbers are going to be the same with potentially different plus or minus sign. Now, if we have just x, it's positive. So cosine and secant are both positive. If we have just y, it's negative. So sine and cosecant are negative. And then lastly, tangent and cotangent, since we take one of them and divide by the other, they have different signs, so it's going to be negative 1. All right, so our chart is halfway done. We now have all of the ones that are over 4 in terms of radians. Real quick, this is one of the reasons why I like radians better than degrees, is look at how easy it's going to be to notice these angles. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. They're all fractions over 4, and they're all the odd numbers. Really easy to remember. 45 degrees, 135 degrees, 225 degrees, 315 degrees. Doesn't really feel like there's much of a pattern there. There is. You're adding 90 every time. But I think that's a little bit harder to spot than the radians. So get used to these, because I'm going to talk about them as some fractional quarters of pi. All right, well, we're halfway done. Let's get the other half. So Kai, there is not a name for these angles. These angles are just what they are. All right, so the next ones we're going to get are the ones that come from the 30 and the 60 degrees. So let me redraw my unit circle. And let's just put one of them on for right now. We'll go with the one that was 30 degrees. That was this guy. And if you go back and you look at your notes, when we developed this one, we saw that the sine was 1/2 and the cosine was √3/2. We got that one from the special triangle. It was actually half of an equilateral. But we already saw that the sine was 1/2 and the cosine was √3/2. So that's why I know that this point on the unit circle is √3/2, 1/2, because it's always cosine, sine. All right, so let's start filling these in. So I'm going to go ahead and just erase on this chart a little bit. And just erase the chart and rebuild it. So we're going to get 4 angles from this point. We're going to get the one that I just drew, and then we're also going to get the ones that are symmetric, that have the same coordinates, just with possible minus signs, that are found in other parts of the circle. So we're going to do 4 more. The first one is going to be 30 degrees, and in radians, that's pi over 6. So that's going to be the top blank. So it should go 0, then 30 degrees, then 45 degrees. And we already calculated these. We saw the sine was 1/2, cosine was √3/2. So the tangent was √3/3. The cotangent was √3. Secant was 2√3/3. And cosecant was 2. So again, go back and look at what we did last time, and you'll see where those numbers come from. Okay, but now we can use that guy to help us find the other ones that have similar x and y values. So if we come over here to the second quadrant, this point right here has coordinates of minus √3/2, 1/2. So the question is, where is that angle? Well, we're going to do the same trick as before. We saw, like in this case, that this is a distance of pi over 6, which means this first one that we're looking at is also pi over 6 away from the x-axis. So we're short by pi over 6. Well, if we were to go halfway around, that would be pi. So we're going to subtract pi over 6, and that gives us 5 pi over 6. Now, 5 pi over 6, that's going to go in the row above pi. So as we're going down our chart, you got to pi over 2, we had a blank, then we had 3 pi over 4, and then a blank. That next blank is 5 pi over 6. Okay, so it's right between 3 pi over 4 and pi. Well, in terms of degrees, let's again just do the subtraction. We're 30 degrees shy of halfway around. 180 minus 30 is 150. So we're going to speed this up. I'm going to copy all these numbers because I know that they're all going to be the same with the possible exception of having a negative in front. So let's just start by copying them all. And now let's figure out which ones are negative. So anything that has x alone is negative. Well, that's cosine and secant. Anything with y alone is positive. So sine and cosecant stay the same. And then tangent and cotangent, since we're dividing these, one positive and one negative, makes those both negative. So the exact same values, just we got a whole bunch of negatives. All right, so there's that guy. So we go to the next one, down here in the third quadrant, where we've got both our coordinates are negative. By similar argument, we're pi over 6 beyond halfway. So we'll take pi plus pi over 6, which is 7 pi over 6. And this is going to go in the row that's directly below pi. So we just got 5 pi over 6. The next one in our chart is pi. Now we're going to go to 7 pi over 6. In terms of degrees, it's 30 degrees beyond halfway. So that's 210. And again, I'm just going to recopy all of these numbers, knowing that the only thing that might change are signs, plus or minus signs. So let's figure out which are which. So now if we have x alone, it's negative. So that's cosine and secant. If we have y alone, it's going to be negative. So that's sine and cosecant. And then tangent and cotangent, since we're dividing these two, we're going to get negative divided by a negative, which is positive. So those two just stay the same. All right, so there are those. And then if we come to the last one, this one we're pi over 6 short of the entire circle. So if we do 2 pi minus pi over 6, that's 11 pi over 6. And this one needs to go into the very bottom blank row. So the second from the bottom on the entire chart, right above 360 degrees or 2 pi, we want 11 pi over 6. Again, in terms of its degree measurement, we're 30 degrees shy of the full circle. So 360 minus 30 is 330 degrees. All right, same story as before. Let's rewrite all these numbers, knowing that the only thing that might change is plus or minus sign. So this time, since our coordinates are positive, √3/2, negative 1/2, anything that has x alone is positive, so cosine and secant. Y alone is negative, so sine and cosecant. And then again, tangent and cotangent, since it's a positive and negative being divided, gives us negatives. So pretty quick, right? Once we knew pi/6, these others we could get very quickly. We just had to pay attention to the signs, the plus or minus sign. Also notice, kind of similar thing we saw with the radians before, all of these fractions have a 6 on the bottom. And in fact, these are all the fractions of 6s if we're reduced. Because if you have any other number of 6s, 2, 6, 3, 6, 4, 6, and so on, those things simplify. So these are the only ones that are going to have 6 on the bottom. All right, so there you go. There are those 4. So we have 4 more to go. 4 more rows to go, and those are going to come from the 60-degree angle. So before I erase this, any questions? All right, so let's go get the rest. Let's get the other ones and fill them in. So on our unit circle, similar picture. It's just this time, since we're at 60 degrees, we're up here. And this is now 1/2, comma, √3/2. Again, go back and look at your notes from last time and you'll see where those came from. They're really found by knowing the 30-degree. We basically just swap what these guys are. So this was 60 degrees, also known as pi/3. And so from last time, what we know is that the sine and cosine are just the swaps of what they were for 30 degrees. So that means that the sine is √3/2 and the cosine is 1/2. Similarly, tangent and cotangent swap. So tangent is now √3 and cotangent is √3/3. And then secant and cosecant also swap. Secant is 2 and cosecant is 2√3/3. All right, so that row should be in your topmost blank row. And we only have 3 more rows to fill. And those 3 are going to fill in with these respective angles. So I'll just go ahead and draw them all in here. So I'm just going to go ahead and put all the points because we know we're going to use them. And we'll do exactly what we did last time, which is I'm going to copy all of this information. So in the remaining blank rows, go ahead and just copy these numbers. We're obviously going to have to change the signs on some of them. Some of them are going to go negative. We will take care of that when we get there. But we're just making use of the patterns that we've seen before and the fact that we can speed this process up since we already know what happens with the 60 degrees. All right, we'll worry about pluses and minuses in a second. Let's first get the new angles. So we're going to do the same thing. We're going to use this first angle to help us. Since that's pi/3, we know that this second one is pi/3 short of going halfway. So we're going to do pi minus pi/3 which is 2 pi over 3. So that angle is 2 pi over 3. And 2 pi over 3, if we convert that into degrees, is 120 degrees. So let's change the signs. So the things with only x go negative. So cosine and secant. Those with only y stay as they are. So that's sine and cosecant. And then tangent and cotangent, since it's a one positive and one negative, those both change sign. So boom, there's 2 pi over 3. Now we come to the one in the third quadrant. Again, we're pi over 3 past half a rotation. So we're going to take pi plus pi over 3. Well, that's 4 pi over 3. So that's going to be this guy. Similarly, if you convert that to degrees, that's 240 degrees. So now this time, anything with an x only is negative. So there goes cosine and secant. Anything with y only is negative. So sine and cosecant. And then tangent and cotangent are both positives because we have a negative over a negative. Whew. All right, last row. What about this guy? Well, this one we're pi over 3 shy of going all the way around. So if you do 2 pi minus pi over 3, that's 5 pi over 3. And 5 pi over 3 in degrees is 300. So this time, anything with only x is positive. So cosine and secant. Only y, we go negative. So that's sine and cosecant. And then tangent and cotangent, same story as before. One's positive, one's negative. So when we divide them, we get negative. All right, so there you go. There is the entirety of that chart. Now, this is a chart that you want to know. You want to be able to know all these values. You want to be able to kind of recall them if I ask you about them. Okay. So looking at that, you might go, oof, there's so much that we have to do. Well, it turns out that there are a lot of patterns, and I'm going to share them with you as we go along.
The first thing that's kind of important about this, or important to notice, is that you can really get away with knowing only the top couple of rows, right? If you've got the top couple of rows, you can create the rest of them by using the symmetry. We actually called those top couple angles, we call them reference angles. In fact, any angle that's in the first quadrant is a reference angle for the others, because the symmetry allows you to find ones in other places. So when you do some reading, you might see something where they'll say, you know, talk about a reference angle. That's just the first quadrant angle that has the same points according to symmetry as the one that you're interested in. So if you know the reference angles, you're good to go. The only other thing we need to remember is how can we figure out which signs we have, plus or minus signs. And there's a pattern to that as well. What I'm going to do is I'm going to share my screen again, and I'm going to show you a completed trig value chart. Okay, so I've got one of these that's already completed that I've written out, and I will put this up on the page so you guys can confirm it, or at least check it against what you've got. So let me just pull it up here real quick. My computer again is being very slow. Or maybe I won't show it to you. I'm getting the circle of death. Okay, good, there it is. So here is a completed trig function value chart. So yours should hopefully look something like this. And I just want to point out a couple things. First of all, notice that the patterns here hold in terms of the different values being repeated in different locations. But what I want to show you first are plus or minus signs. Let's look at the sign column. So notice how it starts positive. We've got 1/2, √2/2, and so on. So we got a whole bunch of positives, and then it turns negative. So the top half of the chart is positive, the bottom half is negative. Cosine, it's a little bit different, but it goes positive, negative, and then goes back to positive. But notice how sine and cosecant, so the first column and the last column, have that same pattern. Positive, then negative. Positive, then negative. Cosine and secant share the same pattern. Positive, negative, positive. Positive, negative, positive. And then tangent and cotangent also share the same patterns. Positive, negative, positive, negative. So if you know the big three, you can get the other three. And we already know that because of the fact that they're reciprocals. So cool. We'll talk about how to actually tell the pattern plus minus a little bit easier in a second. Also, if you know sine, you know cosine. Remember how we talked about these things swap? We have sine and cosine of 0 are 0 and 1, but for 90 it's 1 and 0. For pi/6 and pi/3, they swap. So really, you don't need to know cosine if you know sine, because you can get them just by switching the values and potentially changing some signs. So let me show you a really easy way to remember sine. So you'll notice this pattern. It goes 0, 1/2, √2/2, √3/2, and 1. Well, I'm going to write this up on the whiteboard because there's kind of a fast little way of getting those values. So burn that image into your head. The 0, 1/2, √2/2, √3/2, 1.
And here's how you can get that really quickly. So simple little pattern. We had 0, 1/2, √2/2, √3/2, and 1. Notice that this is √0/2, √1/2, √2/2, √3/2, √4/2. Right? The square root of 0 is 0. 0/2 is 0. Square root of 1 is 1. √2, √3. Square root of 4 is 2. 2/2 equals 1. So there's a real fast way of building the sine values in order from 0 to pi/2. It's 0, pi/6, pi/4, pi/3, pi/2. It's √0/2, √1/2, √2/2, √3/2, √4/2. So there's our sine, cosine, just do them in the reverse order. 1, √3/2, √2/2, 1/2, 0. Well, now that you've got sine and cosine, flip them over. Take the reciprocals, that's your secant and your cosecant. and we're pretty much done. All right. Well, we're
out of time, so I'm going to stop here, but we're going to pick up with this where we left off. We're going to talk about some more patterns, how we can use this chart, some things that it tells us, and specifically we're going to start looking into these things as functions, things like domain, range, you know, all that good stuff. And we'll start working on a better understanding of how these are related. And what I love about this is that it's going to turn out that all you need to know is one of them. If you know any one of the trig functions, you will know every other one because they're all interrelated, because they're all coming from right triangles. So, but I will share that beauty with you next time. So a couple things real quick. We need a word of the day. And I think word of the day, because I happen to have one right here, is just going to be ball. Okay, so the word of today is ball. And I mentioned how you're going to probably want to know those for quizzes and such. We're going to do a quiz next time in class. And the way that this is going to work is we're going to kind of go over lecture, do our usual thing. And then at about 11:30, I'm going to post a quiz up on the Canvas site. It's just going to be a file. I'll send a message that says, you know, with the quiz attached, and you're basically going to have a half an hour to work it out and then get it back to me. You're just going to email it to me, so you can either scan or take a photo and email it back. So we'll do that next time. I will put up a message in the next, well, tomorrow probably, that reminds you about this and how it's going to work, but we are going to have a quiz, and it's just going to be on the first two sections, 7.1 and 7.2. All right, so I will put a message up on the board, on the Canvas, so that you guys know this is coming, but there's gonna be a quiz next time on 7.1 and 7.2. I will release the quiz at 11:30, and then you'll have a half an hour to get it back to me. It should be pretty fast. It's just gonna be, Benjamin, I was just about to say, it's usually about 4 or 5 questions, so not very long, but just a couple of questions, make sure that everybody's sort of keeping up to date. Okay, so we're going to do a quiz next time, and knowing the words of the day might be beneficial. All right, so with that, have a wonderful couple of days, and I will see everybody on Wednesday. And don't hesitate to reach out to me either during office hours or email message or something like that if you've got any questions. All right, so have an awesome couple days, and I will see you all Wednesday.